Okay, great. So welcome to, I guess this is the last of our sort of Friday lectures that we've been doing over the course of the semester. And, I'm honored to be able to speak to you today and talk a little bit about the topic of systems engineering, and I'll sort of give a little bit of intro to what's going on that front. But of course, the big objective of these Friday talks we've been doing is to try to sort of build culture and try to help new students get oriented with what we're doing and try to give everybody some toolkits to be able to be successful in grad school. And so you've sort of seen those topics over the last couple of weeks. And for me, at least, this is a great opportunity to be able to share a little bit about what I hope is some motivating factors, some of the topics of interest for our department. And at least, I'm gonna sort of make some assertions as we go through here. And I'm eager for conversation and sort of a little bit of back and forth or whatever about what we're talking about and whether you find those assertions to be true or not true or valuable or whatever else. Now, when we talk, so just to get us sort of ramped up here again. My name is Tom Bradley, and I'm really honored, of course, to serve as the department head for the newest department on campus, which is our Department of Systems Engineering. I'm gonna sort of blur some lines. I'm gonna play a little wordplay here, which is that the title of the talk and the title of the subject is what is systems engineering? And when I say that, I mean we're going to talk about the field of systems engineering, and we're also going to talk about our department and what we're trying to do in our department space. Okay, so that's sort of the objective here, right? We are now the newest department on campus. We've got a nice little sign with the doorway with 13 people behind it or whatever I was saying. And so the question is, what are we doing? What are our motivations? What are we trying to do here? What's the big picture? What's the role that we believe that Colorado State University Systems Engineering can play in being able to think about these big things? So now, within the context of the question, what is systems engineering then? My goal is to be able to talk about it in, I guess my little beeper doesn't even work. Beep. I have to ask the question, so we're going to say, what are systems? What is engineering? What is systems engineering? And then get back at our big, maybe a bigger question, right? I mean, philosophically, answering the what questions is interesting. Hopefully, answering the why are we doing this is a little bit more purposeful. Okay, so let's talk a little bit about what all of these terms mean, what we mean by them, and why we're trying to do what we're doing here. Okay, so let's start out with the idea, and for those of you who've taken our courses, some of this might be a little bit of review, right? But the idea is, if we want to talk about systems, we need to start sort of at the beginning, right? We need to stay even earlier than when we talk about systems. We need to talk about sort of how do we know things and how do we think about science as the study of knowledge and all these kind of things, right? So we have a philosophy that has just for hundreds of years throughout science, right? Which is called scientific reductionism. And scientific reductionism sort of says, look, if I could take a very complicated thing and I could isolate it as much as possible, I could really come up with some fundamental deep laws of understanding of that little entity. And it's sort of symbolized here by we sort of take a plant from the forest or a crop from the field, and we sort of say, if I could control all of the oxygen that it gets and all the light that it gets and all these, I could come up with a fundamental understanding of what that plant is doing. And this is the way that science has worked for hundreds of years, and it's great. And this has been a foundation for much of what we know about biology and about chemistry and about engineering and about physics or anything else. To me, a classic example of this is the way that we think about temperature. When people were trying to discover the way that they think about, or how to measure, how to think about temperature. Temperature was just an idea of trying to measure sort of hotness and coldness or something, right? And so it has some impact on, when the sun is shining, makes us feel different temperature. whether it's cloudy or sunny, whether the wind is blowing, whether or not we have clothes on or what, there's so many things that are connected to how we perceive a temperature, right? And so when Fahrenheit and Celsius and all those guys, right, we're trying to figure out how to measure temperature, they had to sort of say, okay, that's all so complicated to think about all those things. What I can do is I'll just, I can find this one relationship that is, that with something that I'm going to call temperature, that I'm going to call thermodynamic temperature, it raises and lowers the expansion of this material, et cetera, right? And it's a simplification, but it allowed them to be able to understand something very, very fundamental, far removed from all of the other effects that can influence what we actually sort of perceive as hotness and coldness, right? So it's sort of, that was a sort of roadmap for how scientific method works and how we can think about this idea of scientific reductionism. Now that was, of course, hugely successful, right? I mean, it's sort of like, this is the foundation of all of our technological society and all these things like that, the Enlightenment and Industrial Revolution, and all these kind of things, right? That foundational idea of temperature leads us to be able to build steam engines and stuff. Fundamental ideas about mechanics and materials led us to be able to design big bridges and civil infrastructure and all that kind of fundamental ideas about electromagnetism led us to be able to do all the amazing things we can do with electrical circuits, et cetera, et cetera. So these things are, it's great. But there's also information that we have left behind when we think about things in this purely reductionist point of view. And so we are limited in that reductionist point of view from being able to consider problems where reality bumps up against what we can understand from experiment, from scientific method, et cetera. Just as an example. So, I mean, the main or some primary categories of things that are challenges to the ideas of scientific reductionism are things like, it's called near decomposability, but basically it just means that it's not decomposable. So you can think about, here's a technician operating a nuclear power plant or whatever, right? And if we wanted to try to analyze this situation, we would say, okay, well, from a reductionist point of view, I'll break this apart into the person, the user interfaces, the buttons, whatever they are, right? The switches and buttons, et cetera. And we would sort of say, okay, now I can understand these buttons and switches, perhaps. I can understand these user interfaces, perhaps even more, at a reductionist point of view. But how do I break apart that person? And can I break them apart and gain a deeper understanding of what they're doing, or why they fail, or why they have, when they get overloaded and all these kind of things? And the answer is, you basically cannot. There's limits to how far we can. There's not available fundamental truths around what the interfaces are between all of these components that we can break down. So we sort of are challenged in many situations that are sort of human technical, socio-technical, environmental technical, that we cannot meet that idea of decomposability. Another example is stuff like duality. Everybody knows about, like, the classical physics example of this is the sort of wave particle duality in physics. But there's lots and lots of places where this comes up. I mean, an example, a classical mechanics example, is if you have two bodies that are coming into collision and they're under the impact is under a stick slip friction. We don't know, there's a single friction force that can have sort of dual values of velocity. So we don't know whether it sticks or slips until it actually is both sticking and slipping in the physics of the problem at the same time. It's dual. We don't have an answer to that. This, a sillier example is sort of, we think about requirements or something like that, right? The purpose of a screwdriver, of course, is to drive screws, but it's also to do this other thing, which is pry open paint cans. It's also to do this other thing, which is to, pick my teeth or whatever. It has all of those requirements. And what's going to drive, or what's the objective of a screwdriver? It has to be all those things. Well, that's not really, that violates the assumptions of things like the reductionism, and more, even more fundamental and sort of inclusive of all these other stuff too, is ideas about like complexity. And complexity is the idea where I sort of have some definitions of complex systems up here, where complex systems are those that have a large number of elements in the system. They have lots of dynamic interactions, et cetera, et cetera. They have a weak central rules. Rules are not shared among the components, and rules are independently determined and controlled by the distributed components out there, et cetera. So it's sort of one of these things where we can think about complexity, we can think about randomness. All these things drive us away from being able to consider these things as classical reductionist problems. So lucky for us, and this is, this isn't, it's not revolutionary to say this, right? But we have ways to be able to think about these types of problems, and that way of thinking about these problems is through systems. Now, what is a system, right? A system, we're sort of, when we talk about systems thinking and we talk about defining systems, I mean, systems have these kind of characteristics here. They have components inside of a boundary that defines the difference between the system and the environment. We have relationships in between these components with inputs and outputs and interfaces and interactions between all these components. And this is again, like this is even earlier than being able to think about reductionist thinking. This goes back to the ancient Greeks and stuff, where they understood the idea of systems. We could make hierarchies of angels and all these kind of things like that. So it's not a question of whether or not this is a new and revolutionary way to think about these problems, but it's evolved from the weaknesses, and it evolves as a sort of a technical domain from the weaknesses that we have in thinking about classical reductionist problem sets. So now we can talk now about control systems, feedback control systems. And obviously this is a system, you can sort of see the components. You can see relationships in between them where we have interfaces. You can see what's inside the boundary, what's outside the boundary. This is just a heater feedback control for a house or something, right? And many, many examples of the way that this works. But an important point here is that the systems elements don't have to just be physical. They can be physical, they can be functional, they can be conceptual. The idea is that this is an abstract way to be able to think about problems, be able to define. So now, this is really, so this gets sort of exciting if we get to think about it in this way, because practically many problems that are, again, sort of like not particularly amenable to reductionist thinking can be modeled as systems. We can model enterprises as systems. So I just told you all that, right? Hierarchies and things like that is an example of a type of system. Well, here's an enterprise, the Alameda County Public Health Department, that we can model as a system. We can model the environment, by which I mean the global environment or Earth system. We can model as systems. We can even model engineering activities as a process, as a system, and on and on and on, right? So we have lots and lots of examples of the way that we can think about modeling of systems. So now, the benefit of being able to do this type, being able to sort of have this framework of systems is that we can develop an understanding that is transferable from one type of problem, from one problem domain to another. So for example, this feedback system idea is completely transferable from an understanding of ecosystem dynamics or whatever, ecological dynamics. Everybody's seen the example of wolves and rabbits, right? Where the wolves eat so many rabbits, and there's the dynamic of feedback systems that goes along with that. That exact same relations, those exact same understandings, that same dynamic behavior also applies to a Toyota manufacturing system, automotive manufacturing, right? And so the power of being able to think in this of systems and representation of systems in this abstract term is that we can take the lessons that are learned from one particular domain and we can apply them to other domains that don't have anything to do in this, with the same application. Ecology and technical manufacturing are not, sort of equivalent or analogous domains, except through the lens of systems science and of systems understandings. Okay. So this is the promise of being able to, so this is, I've been speaking perhaps a little bit abstractly here, right? And that's on purpose, because the charge is that if we could look out at the world and we could put it into this framework that is a systems understanding, then what we could do is we can actually help ourselves to understand new domains and new problems and to understand them in some depth. And that's what we were looking for when we talked about reductionist thinking anyways, too, right? We were looking for some fundamental laws, a fundamental understanding that would help us to be able to translate that understanding from one domain to another. It would help us to build, if we understood thermodynamics, then we could build heat engines and these kind of things. Well, if we can understand systems, then perhaps we can engineer them. Perhaps we can build with that understanding. Perhaps we can actually implement these ideas in a technical sense, okay? So now, this is sort of the promise of what system science does. It lets us look at these patterns and dynamics and be able to understand them in that context. So then our next step is to be able to say, okay, now let's talk about what engineering is and see if we can make a mapping between engineering and what I've just been talking about. Okay, so now, again, what is engineering? You might have come across an example definition of engineering that looks like this, and it's actually, this is a definition that's perfectly valid. It's one that I use with perhaps less technical audience and such. But the idea is that what is engineering? It's sort of the study of using scientific principles to design or to build or whatever. And this is a dictionary definition, et cetera. And so what you sort of see is, I got this diagram on the right here, and this is a classical sort of way that people look at engineering knowledge, is that there's, again, in a reductionist point of view, there's sort of like, there's science, and science is the foundation of human knowledge or something, right? And then engineering has this kind of messy role, which is that engineering takes one-way street from scientific knowledge into engineering, and engineering reduces that to practice. Our job is to try to, as speaking as an engineer, our job is to try to take that scientific understanding and engage with the industry and engage with the real world, engage with the technosphere, and be able to actually sort of make it happen. Now, okay, that's okay and all, but it's a little bit, I'm going to assert that this is a little bit of an outdated way to be able to think about what engineers really do and what engineering actually is. So I'm going to sort of say, we're going to reject this definition for the day, and what we're going to use is this other definition. And this definition, I'll read it out loud here or whatever, but is that engineering is the practice of organizing the design and construction and operation of any artifice. So it's a little bit of an old-fashioned word, but all that artifice means is an object or a program or a whatever that transforms the physical to meet some recognized need. And the definition, sort of, I want to include this idea that engineering and science are both autonomous, which just means that they sort of are separate and separately directed forms of knowledge. And okay, now I like this definition better for a couple of reasons. Number one, it sort of, it acknowledges, I'm going to bring up a couple of bullet points here, right? Which I've highlighted. It sort of says that engineering is more than just design, right? I mean, it's more than just sort of envisioning this. It also includes the operation. It also includes construction. It's got a more life cycle bent to that definition, doesn't it? It also, of course, recognizes need. So it says, look, engineering is not about just doing stuff because it's cool, or not just scientific pursuit of knowledge forever. It sort of says we have to identify, we have to recognize, we have to respond to some need. So it's sort of, again, the big point here is that rather than construct a one-way flow of information, of causality from science into engineering into practice, it sort of says, look, engineers are, we have a special role here, which is to recognize the need to be able to translate that need into something that will meet the need, and then to be able to actually operate that for its duration. So it sort of says that, you know, things that we know from science and things that we know from engineering will be different. And okay, so to me at least, there's a couple of powers in those definitions. One is that this gives engineering a broad mandate. It sort of says, look, our job is not just to design and not just to make and then kind of like roll out the door and shut it and hope it goes away or something. Our job is to manage the entire life cycle of need, of this product, of maintenance, of disposal, all the things that we need to do, right? So it sort of says, whereas the conventional definition gave engineers a lot of power in this early, you know, sort of phase where we sort of are taking concepts, and then we take those concepts and we sort of decide, okay, make the dimensions 47 inches or whatever, and then engineers are done. No. Our job, in fact, is that we have to manage the entire life cycle of this product, right? This is one piece of this revised definition of engineering. The other one that I said is that there's a need. We have to be responsive to need. And so what that really means is that engineering is really motivated explicitly, like with at the front of the thing that's driving the bus is need for the betterment of society. So our objective, and when we think about systems engineering, and we think about engineering in general, is not about toy problems, and it's not about pursuit of knowledge for knowledge's sake, and it's not about I don't know, just spending money because the National Science Foundation gave it to us or something. We have to actually be responsive to the needs of society. And of course, engineering is driven by a set of needs, and then those needs are adapting. Those needs are changing. Those needs are evolving, right? So it might have been a number of years ago that we didn't consider engineering for equity or something like that, or engineering for social benefit to be a valid source of need for engineers. I mean, I can tell you from experience, no longer the case. Whatever our judgment on that might be, that is not the case anymore. Now, those are part of the requirements that we are going to have to meet to be able to define need for engineering. Okay, so so now you can sort of get a little bit of the flavor here, right? Which is, we've talked about systems and what the sort of power of systems are. We've talked now about engineering. And when again, my goal in talking about it and defining it in the way we have is to insert into our consciousness this idea that engineers have a specific role. It is a specific role to be able to generate technical knowledge, to be able to implement that knowledge, of course, in practice. But it's not, the job is again, it's independent of science. It doesn't have anything to do with going out and making, I don't know, whatever, like fundamental discoveries about the way that plants grow or something. It's that we have a job to do, and it's not, and it's really driven by this goal for society's benefit. Okay. So now we get to maybe the fun part, which is, if we know what systems they are, if you accept my definition of now, this revised definition of what engineering is, now we're going to plug these together, and you see the writing on the wall, which is we're going to now be able to talk about what systems engineering is. All right, let's give it a shot. So let's start then again with a contrast to disciplinary engineering. And by disciplinary engineering, I mean mechanical and civil and aerospace and whatever else. So let me present to you that idea in this kind of graphic here, which is modified by from a classic text on systems from Weinberg. And the idea of this is that I sort of adapt it in order to be able to place on there engineering technical activities. So what this graphic sort of shows is on the horizontal axis, we have complexity, which we've already kind of talked about. We've defined a little bit. On the other axis, we have something that's sort of like randomness, okay? And randomness is just another, everybody knows randomness, right, is that under repeated trials, we get different answers. So we can think about that and we can sort of map problem sets onto this region of, that shows complexity and randomness. And what you sort of see here is Weinberg classifies these things into complication, complicatedness, systems, and just kind of so chaotic, so complex that you almost can't do anything about it, okay? So what does complicatedness mean? Complicatedness is the region of machines is what it's called. And what that means is that it sort of says, hey, a car, for example, how many parts are in a car? I mean, 100,000 parts in a car or something, right? Very complicated machine. But we know how to engineer a car. We take all the parts, we make big catalogs of them, we design them with a team of thousands, and we put them together, and the car drives off the end of the line 1 per minute every single day of the year, all year long in Detroit, right? That's just what they do. We know how to do that. And so if you think about, like mechanical engineering is that lower right kind of brown bullet there. We know how to do complicated stuff. And I could think of problems, I sort of tried to think of problems that were very random, but not very complex. That might be like statistics problems, right? If you had a statistical problem, that's a very random problem, not very complex, but we know how to handle that. We have a tool for that. It's called statistics. It's not that big a deal. On the other hand, like let's say ocean engineering. Ocean engineering is a topic set that is significantly complicated by the fact that ocean engineering loads are so high, and there's so many random things that happen, and there's you can get interactions that are nonlinear and complex because of things like the excitement from the waves and from the wind are so varied in their frequencies and all these kind of things like that, right? Okay, so I'm sort of making the case that boy, oh boy, but as we get closer and closer to that boundary, we sort of lose the ability to engineer those systems in disciplinary terms with our conventional reductionist thinking. On the other hand, let's go all the way to the upper right. And so that's sort of like this unorganized complexity where everything is fighting each other all the time. And I mean, you think about war or disaster relief, and these are things that basically just need to be managed. We almost can't really engineer them, but we can manage them for maybe minimizing damage or something like that, right? But in between is this region of systems, as Weinberg defines it. And it sort of says, hey, these are places where it's too random, it's too complex for us to use our conventional tools. So how are we going to engineer these things, right? These might be things like human machine systems. These might be things that are big DoD acquisition systems, smart grids, cyber physical systems, autonomy, all these kind of things like that are problem sets that if you try to engineer smart grid using only electrical engineering tools, you will inevitably fail. You can't do it, right? It has too many humans in the loop. It has too much economics in the loop. It has too much feedback system. It's too complex to be able to do that. Okay, so the point is, well, do we give up? Does that mean like we just don't get to do smart grid? It's a pipe dream and we just never get to do it? No, and not so. In fact, the reason that we call this the reason of systems is that our goal is that systems engineering is the toolkit that we can use to be able to address problems that are in the region of systems. It doesn't necessarily, we make no promises that we're going to be able to solve every one of those problems, but it means that we can make progress towards them using our systems engineering tools. What are those tools? What are the characteristics of systems engineering that makes it able to do this stuff? These are things that, again, if you're going through our program or taking the 501 class or something, these are going to be very common ideas to you. But I'll say them out loud and follow up on them here. So systems engineering sort of concentrates on the design and application of the whole rather than the parts. So again, if I was as a mechanical engineer and I needed to design a particular you know, component for a car or whatever, or I need to design a car, I would go piece by piece by piece by piece and design every single little part. And then, you know, I'd have to hope that they kind of matched together and got this done, right? Systems engineering, on the other hand, concentrates on the design of the whole. So whereas civil engineers need to think about the dam, systems engineers are concentrating on the needs and the requirements and the interfaces for the entirety of the water supply and use and recycle system, right? So we sort of say, you know, that's what my diagram on the right there sort of represents. Now, that gives systems engineers a unique responsibility. It means that systems engineers, of course, are responsible for the function of the car, that there are hundreds and hundreds of mechanical engineers all working on brake systems and steering systems and all these kind of things like that. And then the systems engineer has to make sure they all work together. But it also means that we you know, there's no such thing as a ethical dam. A dam doesn't have really ethical powers to it or something. It's just an object, right? It's just a component. What does have ethical power is the entire system, right? We can ask, you can't ask whether or not the concrete of the dam has, you know, has ethics associated with it. You can ask whether or not the system is ethically constructed and operated, whether or not it, you know, whatever, displaces people or is environmentally responsible or all those kind of things. Those are questions that we have to ask, not of the object, but of the system. And so that means that systems engineering has a particular role to play when we think about those big questions of what is sustainable, what is ethical, what is technically feasible, et cetera, et cetera. Those are questions that we really can only answer as systems engineers. The second bullet point that I had out there was that systems engineering considers both business and technical. So again, like the question is, what makes systems engineering so special? Why is it that we can actually do that engineering in the region of systems? The second reason is because we have to consider both business and technical processes. So again, I sort of assert here that it is a responsibility of all of us who are engaged in the engineering enterprise to be able to take innovations and not just hold them close and not just put them in our pocket and not just say that we're the smartest person in the room, but to be able to actually translate those innovations to practice. And so that's, you know, again, that's to me, the idea of that is that means that we actually have to work to be able to do those things. It doesn't come naturally to all of us. It doesn't come that, you know, you just can kind of like drop my, you know, I wrote a beautiful 25-page paper on all the awesome stuff that I'm doing. And I just drop it right there and let everybody go to town, everybody. It's going to be great. No. Our charge instead is to actually be able to do the work to be able to make this in practice. So that means that systems engineers need to operate within enterprises, within governments, within management to be able to meet the needs that we have. And it means, so to do that, it means we have to be broader than a conventional engineer, than a disciplinary engineer. We also have to understand agreement processes, project processes, organizational processes. Lucky for me, I don't have to make this up. Those are exactly the words that are in the Systems Engineering Handbook from INCOSE, right? So this is a universal understanding of what systems engineering is about. The third bullet point here is that systems engineering is, of course, transdisciplinary. Every systems problem that we were talking about really lies at the intersection of disciplines. And I was seeking ways to put this term more often in this presentation, but in teams. It's at the center of disciplines and it's the center of teams. So systems engineers, of course, in order to be able to think about these problems, in order to be able to solve them, in order to be able to understand those interfaces, we need to be able to move within disciplines and doing all this kind of stuff. So now we get to, you know, I'm going to sort of try to now bring this back to our talk about what we're doing in our department here. Our program is really seeking to transform engineers that are, you know, what we call sort of, and this is, you know, again, just sort of a term for it, but it's like I-shaped engineers. And what is an I-shaped engineer? An I-shaped engineer is a great student, did all the work everybody asked for him, and got a Bachelor of Science in civil engineering or something like that, right? They can design the concrete, they can make the steel, they can do the things, they're deep in their particular domain. But our objective is, we sort of, it's easy to assert again that we cannot, that's not, that type of skill set is not amenable to being able to solve systems problems. So to be able to solve systems problems, we need to be this transdisciplinary person. We need to be able to understand that a disciplinary background is only the prerequisite to being able to have multiple disciplines of expertise mated with system thinking and analytics and design and all the things that we can teach, all the things that we can exercise. It's not a download from the department, but all the things that we can exercise in graduate school to be able to build ourselves into these M-shaped engineers, right? Which is just an analogy that sort of says we have multiple prongs of depth united then by this breadth that allows us to be transdisciplinary. Systems engineering considers the entire product lifecycle. So I gave you that I talked already about the engineering lifecycle. The engineering lifecycle, you will recall, was all the way from requirements to disposal. But it sort of says, look, engineering lifecycle is one component of a technical, social, environmental problem. When we think about a technical, social, environmental problem, we need to think about all of those aspects and what those life cycles are in all of those domains. And so we need to understand that there are constraints of sustainability, of social license to operate, of all sorts of things that mean that we need to be, it's sort of, we all understand it, it's obvious now, right? But we need to be thinking about sustainable systems. We need to be thinking about the entire life cycle of data if we want to think about security. We need to think about the entire life cycle of a society if we want to think about safety. So the idea is that systems engineering allows us to have these tools wherein we can think about the entirety of the product life cycle. And that gives us, again, a special role in the technical domains to be able to think about those problems. And then the last one I sort of have here is that, that systems engineering is really based off of systems thinking. Now, what is everybody who's taken we have a systems thinking course right now. It's just was offered for the first time last summer or something. So perhaps some of you guys have taken that, but the idea is that what is systems thinking? It's modes of thinking that allows us to consider the components, the relations, the context, and the dynamics of a system. So just so happens, of course, those are exactly the things that when I had that diagram, we had components and relationships, and environments and interface. That's exactly what systems thinking is about. It's sort of using a couple of modes, using a family of modes of thinking to be able to help ourselves to do that work. Some of it is words that you will have heard before. Perspectives, getting different perspectives. That's a mode of systems thinking. Dynamics is a mode of systems thinking. Modeling and thinking about various fidelities of models, in this case, is a way of systems thinking. So the point is, this is something that is a key skill set that we try to train when we think about systems engineering, because it gives us a way to be able to understand, to be able to look for those common patterns, to be able to communicate fundamental understanding, fundamental knowledge about systems for the betterment of the entire technosphere. Okay, so then the last sort of point here is that now the big idea is that when we talk about systems engineering here, the outcomes of systems engineering is we're seeking this deeper understanding of the technical world, right? So it's just, our objectives are the same as when we were talking about reductionism. We're looking for the patterns, we're looking for the characteristics that unite and that can help us to learn about problems, whether it's in whether it's in the domain of aerospace or the domain of energy or the domain of socio-technical systems or whatever it might be. Our goals are to be able to develop as engineers. We're going to try to innovate. We're going to try to develop new and reusable and effective patterns of structure or behavior that can help us to engineer new systems. It's going to help us to understand, or again, at least manage complexity in design. And we're going to be able to quantify these trade-offs, quantify our understanding of the problem, even among considerations that are cross-disciplinary and disparate and all these kind of things. the big goal then is to be able to improve the performance, improve our sort of adherence to needs in what would otherwise be intractable problems. Okay, so now last quick bullet point here then is why systems engineering? What are we trying to do at Colorado State University? Okay, so just taking a step back again, the big idea here is we live in a world of systems problems, right? Whether it's global environmental problems, this is metrics of the cost performance of the DoD contracts just going up and up and up means we're sort of getting bad at engineering big systems. And even metrics like, the economic impact of cybercrime right now in the United States is between 1% and 4% of GDP. We lose 1% and 4% of GDP is cybercrime right now, right? These are big systems problems hurting us all the time. We have lots and lots of evidence from industry that we are, that systems engineers are under great demand. And when Dr. Siga, who I'm sure you all have met at least in the classroom, started this program at CSU more than 10 years ago, he really came he came from the Department of Defense where he served as undersecretary. And he really believed that the US was not training the right people to be able to solve these problems. And he looked around and sort of said, we need to start a Department of Systems Engineering with the objective of now training the people who can actually solve these problems. And he really believed that systems engineering is going to be key to the economic and security competitiveness of the United States in the future. We can all look at the trends, right? Which is that whether it's, let's say, in the domain of manufacturing, for example, whatever, right? The United States needs to stake out a special niche and for us to be able to maintain manufacturing economy in the United States. And it's probably not going to be like low thinking, just rote manufacturing. It's going to have to be in innovation. It's going to have to be in sort of low volume, high mix types of applications, which is where systems thinking is going to dominate, right? So for us, it brings me back, and my hope is that it brings us back to the department and to the, I share with you here the mission of our department in the context of Colorado State University. And now what I really hope is that we've kind of gone through, and you see many of these key words, many of these key concepts in the mission, the way that we kind of think about it. Our goal is this interdisciplinary education. It's aligned with, you all may know, Colorado State University is what's called a land grant university. It means our objectives are not only to develop knowledge for the betterment of the library. It means that our goal is to develop knowledge to share with the world. It means we have a service mission, we have an extension mission that is unique among universities. And so it sort of says, we have to make this program accessible. We have to make sure that we're training students that can go out and actually make a big difference. Our objective is to be able to get this, you sort of see the key words here of systems thinking and adaptable and broad student, scholars and professionals, et cetera. And the big idea is that our goal is not just to solve problems or not just to make beautiful equations that we can use to write better papers or something, but our objective is to try to solve the problems that face the human condition. So this is the charge to us all here, right? Which is for giving you, again, the big goal is give you a little bit of background into what is this big topic of systems engineering. Why do we think about it the way we do? And just for you all to understand that these are the topics, these are the sort of set of problems that motivate us. And again, the 13 people who are behind the wall there in the systems engineering office. And I hope that they're also the things that you guys can be motivated with, and that will go out and should take the charge and go out and solve together. So with that, I say thank you so much. Glad to be able to talk to y'all, and I'll be delighted to take questions. Thanks. So you're going to help me with questions, Catherine, if needs be? Great. Thank you. Oh, yeah, eager for input or anything else. No change.
How long has the program been a department? Did it start?
2 years, 2 years now. So the program started in 2008 or so. And then it was sort of this interdisciplinary program of the College of Engineering. And then just 2 years ago, we sort of started up as a department. And again, perhaps that doesn't mean that much to folks who are outside of the university world or whatever, but it sort of is representative of a normalization of the program and deep investment from the university. It sort of means that as you understand, I mean, the university works at kind of glacial scale, of course, usually, or glacial time scales. And so it sort of means this is a long-term, multi-decade investment in the Department of Systems Engineering. So it's really great.
Hey, Tom, it's Bo. Just great. Enjoyed listening, and thank you for your energy in putting this together. It might be just something that maybe you could address just quickly, and that is, where do you see as we push towards the systems engineering kind of purpose and mindset that you've laid out, some of the key relationships within the university and perhaps within industry? Do you see any key spots or key relationships that we've built or maybe we need to build in order to kind of, get to this M shape that you refer to?
No, thank you, Bo. So I'll speak to that in a couple different ways, perhaps. I mean, one thing that you see here is, and I hope I communicate, is that the program is really about a sort of a deep engagement with society and with industry and with government and these kind of things. So that's that's why we're so excited to be able to work with students who are working in the professions, is that we can actually really engage with real world problems. I mean, it would be one thing for us to be able to sit down at our table and pull out my yellowed pad of equations and start writing equations or something. And that's fun and all, but more exciting for me, and I think more exciting for all of us, is to be able to understand what the problem sets are that our students are facing and our industrial partners are facing, and be able to work on those. So certainly, like an industrial and an outward facing orientation is absolutely intrinsic to the work that we're doing. In terms of inside the university stuff, I do think that, we have strong relationships, and some of it again comes out of the fact that we're sort of just have to play this transdisciplinary role. But we do have faculty from a variety of departments across campus that are engaged with us. I mean, dozens and dozens of faculty. I think there's a role at, I'll say at universities in general, at getting better at these sort of system sciences. There's we at Colorado State University have some institutional expertise in things like environmental science and earth system science and atmospheric science. And these are very classical system sciences. So I think there's an opportunity for us in the department to sort of leverage and get inspired by many of those other parts of the university that are also doing sort of system science, and that need to now be able to think about what the management and solution set and all those kind of things to those problems are. So that's always what comes to mind for me when I think about relationships inside the university to be leveraged. So.
Thank you.
Hello, Dr. Bradley. Thank you so much. I'm not sure whether you can hear me. This is Mo.
Hey, Mo, how's it going?
It's going great. Thank you so much. I really enjoyed the presentation. I've been in the program for more than 3 years, and it's always great to update your thinking and understanding about system engineering. So my question is that there has been an old debate within the project management community whether a project manager should be technical expert in the field that he is managing a project for. I really like the concept of the M-shaped system engineer, and I would like to ask you the same question from your perspective, Dr. Bradley. How much disciplinary engineering do you think a system engineer needs to have in order to manage a specific system engineering engagement or project? Do you think that if someone has the system thinking, analytics, and have a very good management expertise and have strong modeling and simulation, do you think that if he doesn't have strong disciplinary engineering expertise in that field, do you think that these other pillars, if you will, could compensate his lack of strong knowledge in the disciplinary engineering pillar?
Yeah, sure. And I think, I mean, probably the default answer to that is going to be, it really depends on the projects and stuff like that, of course. But, to me, at least what I can bring up in that context here is that I really do believe that, for example, many of the sort of skill sets that one gets out of disciplinary engineering are not really sort of disciplinary focused necessarily. There's a lot of similarity between what a mechanical engineering Bachelor of Science student learns and what an electrical engineering Bachelor of Science student learns. And there are things like analysis, and there are things like, how to guess and check, and how to do all these kind of things like that are the important skill sets when we're trying to make progress against these, again, sort of like reductionist engineering problems. Now, I tried to, in my M-shaped diagram, I hope you might have noticed, I mean, I sort of didn't put like electrical engineering, mechanical engineering, and civil engineering as being the thrusts that would be downward facing out of that. I think that those are similar enough that probably that there's lessons that come out of one that are adaptable to another. So when I built those, and maybe I should just I could go back to it or whatever, but when I built those pillars that are the depth pillars, my objective was to put more something like management or more modeling and analytics or these kind of things like that those are places where some depth will really pay off. And then at least to me, I sort of approach your question though by thinking that I don't think that the specificity of those disciplinary domains of engineering or of technical skill or something like that are as important as perhaps what maybe like your default assumptions might be. So I don't know. I mean, yeah, but eager for your insight. You all have just as much insight as I do in these kind of things. The only other thing I'll say on that front I was going to bring up is, this is one of the reasons that our program is really concentrates on graduate education. We sort of view again that there's many disciplines in which students can develop that depth, whether it's computer science or whether it's engineering or whether it's management or whether it's chemistry. Doesn't matter too much. But upon that foundation, then we can build a set of skill sets and a set of other depths that are more systems engineering centric that I think actually serves the student better than if we were just training 18-year-olds to be systems engineers.
Great. Thank you so much, Dr. Bradley.
Great. Dr. Bradley, I suppose I will ask the inverse of those questions, which is, do you think there's a role for teaching undergraduates or exposing them to systems thinking and stuff to make them better as engineers when they enter industry?
I think there is. This is something that we are trying to work on actively as well. Okay. So some of it is, but I think the way to approach that, the way we talk about approaching that is by getting sort of systems thinking activities into like senior year classes kind of things. Being able to get them into, even things like data analytics and statistics courses, that's a place where students can be, approached with thinking sort of stuff. And I think it can actually make an impact on them. It's easy to say, and I think it's absolutely true, that, many folks who are trained as disciplinary engineers will move through their career into being systems engineers at one point or another, right? And that's great. That's natural progression. It's positive, et cetera. But so we want to give them a baseline toolkit, at least an understanding of what the problem set is that they're going to be working with. So that's the kind of thing that we do. There are programs that are industrial and systems engineering programs for undergraduates. We just don't do that necessarily here at CSU. Yeah.
Training positive folks, as one of those, right? Everyone's gonna meet. We, not being in environment, struggle and some of those things. And, some of the comments you made, I really liked your chart you showed on which problems are specific to systems. But how do you find addressing PhDs in mechanical engineering or electrical engineering and telling them the value of systems engineering and why systems engineering has more value than them to tackling those kind of problems? Like, how do you convince them the value of formal education in SE versus they, we've encountered, or I have a lot of, well, I can take professional development classes in that, and I'm a systems engineer. I don't need to have a degree in that.
Yeah, well, okay, so, when we think about doctoral degrees and such, I mean, what is that really about, right? It's about research. And that's the skill set that we're trying to get and trying to develop when we talk about doctoral programs. And so research in systems engineering is, of course, has a different orientation than research in mechanical engineering. Again, and in my opinion, the essence of research activity that is in systems engineering is sort of to be able to push the frontier of systems engineering, right? To push with the knowledge base that we have of systems engineering. And on the other hand, if you're doing a doctoral degree in mechanical engineering, is to be able to push the domain in mechanical engineering. So, I'll speak as my PhD degree is in mechanical engineering. And it took me 10 years or something like that to feel confident enough in doing systems engineering that I could come over here and teach and do research and all these kind of things like that. But it actually takes a switch in orientation, because the objective is not really, again, to sort of dive deep into a particular component and understand that component with great insight or something like that. It's to be able, it's that we're looking at this at a systems level. We're sort of trying to modify the way people design, and we're trying to modify the way people develop requirements, and we're trying to change people's minds about what the performance of some particular system is or something. So I think that there's adaptability that's built in to a research process. I would say at a research university like CSU, even if you got a degree in chemistry or something, what you're really trying to get is this skill set to be able to build your career around R&D activity one way or another. But that doesn't, so I sort of say the orientation is different, the results are different. I don't think that precludes a systems engineer from doing research in chemistry, and I don't think it precludes a chemist from doing research in systems engineering. So maybe not, it's, a pretty soft answer for you, maybe, Trey, but yeah, that's. Well, we're probably out of time. So again, I'm very grateful for everybody's participation, both in the online world and folks on campus here too. And just delighted to be able to talk to this audience. So thank you.